Earlier this year, I published a paper called Extending the Algebraic Manipulability of Differentials. In it, I made the claim that you can do what many books claim that can't be done. You can treat differentials as if they were algebraic and cancelable units. What do I mean by this? Well, most of you should know that in calculus, if you have the equation y equals x cubed, then you can say that dy over dx equals 3x squared. All right, so that's not controversial. These are known as differentials. So a differential is an infinitely small change in a variable. That's infinitely small. And we distinguish this from things like, say, delta y or delta x, which are finite changes. They may be small, they may be large, but in any case, delta y and delta x are finite, while dy or dx are infinitely small. And so when you take a derivative, what you're saying is that 3x squared, so at any particular x position, the ratio of infinitely small changes of dy and dx are going to be given to us by 3 times the current x value squared. Okay, so let's say that I'm at x equals 4, then the slope, the infinitely small ratio of changes, or the ratio of changes between infinitely small values on the y and x scale, is going to be 3 times 4 squared. It's going to be equal to 3 times 16, and that's going to be equal to 48. Okay, so that's the slope. The slope is in fact, that's not just the slope, that's the instantaneous slope, and that's the ratio between any infinitely small change in y and any infinitely small change in x. Okay. Now, historically, it's thought that starting in the 1800s, that we should no longer use infinitely small values, that they were not sufficiently rigorously defined enough to use. So that's when we started getting limits. And so instead of dy over dx each being separate values that are infinitely small, we started getting basically, this was just a substitute notation for the limit as h goes to 0 of f of x plus h minus f of x all over h. So this became the new way of understanding derivatives. And so no longer is this a ratio of values, which are differentials. This is now a ratio of where we're taking the limit where the denominator is heading to 0. And it was thought that treating differentials as actual values was actually problematic. And I'll show you why. The problem doesn't exist until you get to the second derivative. Most of you have actually probably used the first derivative in an algebraic way, for example, when doing integrals. So if I want to integrate 3x squared, if we go back to our equation, dy over dx equals 3x squared, then if I want to integrate it, then I have to move the dx to that side. So I will get dy equals 3x squared dx. And so then I will integrate both sides, and I'll get y equals x cubed plus c. So to do this, you actually have to multiply dx by both sides. Now, a lot of people say, well, this is really more just a notation. We're not actually multiplying dx by both sides, but for all practical purposes, you are. With the chain rule, a lot of people view the chain rule. If I have dy over dx and I have dx over dt, then these guys can cancel out, and I will get dy over dt, and that's been an explanation of the chain rule in some circumstances. So you can see that in the first derivative, differentials are not, they're at least somewhat understandable. But so why is it that people claim that differentials can't be used, there's a lot of people who do claim that differentials can't be canceled this way, that this is just a trick of notation, and that we really shouldn't think about it that way. So why is that? Well, the problem comes in the second derivative. So again, let's go back to our friendly y equals x cubed. Okay, so the first derivative of that is dy over dx equals 3x squared. And the second derivative, you may remember this notation. And this notation is kind of hard to say, but it's equal to 6x. Okay, so starting in the second derivative, you get these funny differentials like this. Now this differential, just to be clear, this actually means dx squared. Okay, so that's how that associates. So let's say, so this is all fine and dandy, but let's say that we had another, that we figured out that x had a relationship to the variable t. And so let's say we have x equals, I want to write capital just because otherwise it looks like my pluses. Okay, so now let's say we have dx dt equals 2t, and then we'll say d squared, it's not really squared, but x over d t squared equals 2. So just to note, this is squared. This actually means a repeated process. When I say d, I might call it squared, but when I say d squared x, I really mean the differential of x, because dx, you'll sometimes see it written where the d is not italic, but the x is italic. And the reason for that is that the d is somewhat of a standard operator, means differential of, and the x is the is the operand. So just like you might have sine x written like this is equal to sine of x. When I say dx, that's equal to the differential of x. And if I say, and unlike sine, because if I say sine squared x, I usually mean sine of x squared. If I put that 2 here, which I will say d squared x, but I don't really mean squared, it's equal to applying the differential operator twice. That's what that means. And that That's a problem with mathematics just because we only have so many places we can put numbers and we run out of them, and so we have to reuse them. It'd be nice to stop having to do that, but that's where we are. Anyway, so let's go back to our equations. We've got these two nice equations. Let's say that we're both talking about the same y's, x's, and t's. So what is the problem here? Well, so let us say that these differentials could be treated algebraically. Well, that would mean that if we wanted to figure out what, if we wanted to know what this differential, d squared y over dt squared was, well, if we're going to do this algebraically, we have a differential d squared y over dx squared. So we could find this value by multiplying this value by dx over dt squared. Okay, because that would give us d squared y over dx squared times dx squared over dt squared. And if we cancel, then that would give us what we're looking for, d squared y over dt squared. Right? And that sounds great, it looks great, but what happens when we actually do it? Well, when we actually do it, we get, so d squared y over dx squared is 6x. Actually, I'll write it under. So this is 6x, and dx over dt is 2t. And we're squaring this to match that. And that's going to equal to 6x times 4t squared. And so since x is equal to t squared, as we can see up here, then that means this is equal to 6 times t squared times 4 times t squared, which is equal to 24t to the fourth. There's only one problem with this. If we do the substitution at the beginning, so instead of saying y equals x cubed, we're going to say y equals t squared cubed, because again, x equals t squared. So we're going to say y equals t squared cubed, which is the same as t to the sixth. So what happens here? Well, that means dy over dt equals 6t to the fifth, which means that d squared y over dt squared equals 30t to the fourth. And those two answers are in contradiction to each other. So that is why people say that you can't use differentials algebraically. Now they've come up with a rule, and it's called the chain rule for second derivatives. And the chain rule for second derivatives will allow you to combine this equation and this equation. And by that I mean this whole box. So I should say this set of equations and this set of equations to come up with a to come up with this answer. But The problem is that it makes a mockery of the idea of differentials being algebraic units because they don't cancel at all. And when you try to cancel them, you wind up with contradictory answers like this one. So is there a way to fix this mess? And actually, there is. So I realized when I was trying to teach the notation for the second derivative to my students that there was a problem. So let's go back to our friendly equation, y equals x cubed, and let's take the derivative. So we'll get dy over dx equals 3x squared. Now, here's the question. So we know that the next derivative is going to be 6x. But when you do things to mathematical equations, you do them to both sides. And so what actually is the derivative of dy over dx? And I puzzled over this for a while because I was trying to explain to my students how we got this funny notation. And so I went and I looked in numerous calculus textbooks searching for an explanation, and I found that none of them had a worthwhile explanation. Most of them just said, this is the notation, don't ask questions, or this is the notation. It shouldn't be treated literally, just used as a notation. I'm like, this is crazy. Why are we going to, I mean, it's a funny looking to begin with. You've got the 2 next to the D, but not on the bottom, and so why are we writing it in this funny way? And we're writing it as a fraction, so why are we writing it in this funny way if that isn't what we mean? So I went on a quest to kind of try to rederive the notation myself. And what I figured out was that the notation is actually the problem. This notation is actually wrong. So to understand what the right notation is, we have to ask ourselves, if we didn't think that these guys were differentials, what rule would we use? How would we go about taking the derivative of this? And I realized that this is an instance of the quotient rule. So what we need to do is use the quotient rule to take the derivative. So the quotient rule is you take, now in order to do this, we need to modify our method of doing derivatives slightly. So typically when we do derivatives, we say, y equals x cubed, therefore dy dx equals 3x squared. Well, that's actually 2 operations in one. That is finding differentials and then finding the derivative. Okay, those are 2 separate operations in my book. The first operation with differentials is, so let's say we start with y equals x cubed. So the first thing that we do is we take a differential of both sides, and differentials will always only be in terms of the variables that are being taken differentials of. So in the case of dy, this is just an alternate notation for dy. So this instantly goes to dy, and this we use the power rule. But we use our rules slightly differently because since we're taking differentials, this becomes 3x squared dx. Okay, so you can see my video on refactoring calculus for a little bit more explanation of how this works. So once you have differentials of all of everything, you can then solve for the derivative. In this case, the only thing that we need to get the derivative, which is dy over dx, is divide both sides by dx. And these will cancel, leaving us dy over dx equals 3x squared. Okay, so therefore, if we're going to do the derivative of the derivative, I want to take the derivative of dy over dx is going to be the same as the differential of dy over dx divided by dx. Just like here, we took the differential and then we divided by dx. That's going to be the same set of operations we do here. So how do we do this? Well, this is going to be equal to, we're going to use the quotient rule here. So the quotient rule, you take the denominator, multiply it by the differential of the numerator minus the numerator times the differential of the denominator all over the denominator squared, and this is all over dx. Okay, so that's kind of a crazy set of things, but we can simplify it because we said earlier that when we say d squared y, that's just equal to differential of the differential of y, which you can also think of, since this is just dy, the differential of dy. So we can replace all of our differential of differentials with this notation. And likewise, since we're dividing by dx squared and then dividing by dx again, we can replace all that with all that over dx cubed. So that will give us dx times d squared y minus dy times d squared x. So this is still kind of a bit of a nutty fraction, but if you mess with it a little bit, you can reduce it to this fraction. You can get it to d squared y over dx squared minus dy dx times d squared x over dx squared. And this is what the notation for the second derivative should be. And it's a little crazy, but it works algebraically. So let's take a look at how. So again, let's go to our equation, and this is, hopefully I can fit this whole thing on the screen. Y equals x cubed, dy over dx equals 3x squared. And now we're going to use our new notation for the second derivative, d squared y over dx squared minus dy dx d squared x over dx squared equals 6x. And then on the other side we're going to say x equals t squared, so dx over dt equals 2t, and we're going to have d squared x over dt squared minus dx dt d squared t over dt squared equals 2. Okay? So now, if we want to know the second derivative of y with respect to t, that's going to be, what we're going to be wanting to find is d squared y over dt squared minus dy dt times d squared t over dt squared. So this is going to be our goal. And we're going to find that we can actually, when we manipulate these equations, we're going to be able to manipulate the differentials algebraically to wind up with this. Now we have to remember, again, that when we say d squared y, we're not actually squaring anything. This is the same as d of y. So just keep that in mind, because otherwise you'll get confused and try to cancel things that you can't. We mentioned earlier the chain rule for the second derivative. And so that's still useful, not because we need it to tell us that we can do it, to tell us that we can make these things happen, but just because the chain rule for the second derivative will tell us which operations we should do in order to make this algebra work out. Because going from this guy to this guy, not that guy, sorry, to this guy is actually really, really ugly. It works algebraically, but it's actually pretty ugly. The way that this works is that, let me just write it in prime notation. So if we view this as y prime, no, this is y, this is y prime, and this is y prime prime, and let's say this is x prime, and this is x prime prime. Okay, well the chain rule for the second derivative says that we can get this guy by doing y prime prime times x prime squared plus y prime times x prime prime. Okay, that's what the chain rule for the second derivative says. It's the chain rule for the second derivative. And what we'll show here is that, and it's ugly, I apologize, but it is what it is that it will actually, the differentials will work out algebraically. Now we can do it, we can compute it right here, just to show you that it's working normally. So y prime prime, that's going to be 6x x prime squared, and that x is that, x equals 2t, or not 2t, x equals t squared, so that's going to be 6t squared times x prime is 2t, which it's squared, plus y prime, which is 3x squared times x prime prime, which is 2. Okay, and that gives us on here 24t to the fourth plus an x squared, that's t squared squared, so it's going to be 3 times t to the fourth times 2, and that's going to be 24 t to the fourth plus 6t to the fourth, and that's going to be equal to 30 t to the fourth. And so this is what, this is the answer we were trying to get originally. When we actually wound up with this guy. But the true answer was this guy. And so you can see the chain rule for the second derivative really gives us the correct answer. So now let's show how the differentials work out. And that is uglier. So we're going to have d squared y over dx squared minus dy dx d squared x over dx squared. So that's y prime prime. Then we're going to multiply that by dx dt squared, which is that guy, and add to that dy over dx, which is that guy, and multiply him by d squared x over dt squared minus dx dt d squared t over dt squared. All right, so that looks awful, right? But let's go through it. Okay, so first of all, we're going to distribute this squared. So this is going to become, we're going to just scratch these out, dx squared over dt squared. So that's going to make our lives a little bit easier. And so let's first start by multiplying these things through. So we're going to have d squared y over dx squared. We're going to multiply that term by this guy, dx squared over dt squared, minus dy dx d squared x over dx squared. And again, we're distributing this guy, so we're going to put him here, dx squared over dt squared, plus, now we're going to distribute this term, dy dx times d squared x over dt squared, minus dy dx times dx dt times d squared t over dt squared. All right, so now let's cancel some things. All right, so we can cancel these differentials. We can cancel these differentials. We can cancel these differentials. And if you look carefully, you can see, so this is a plus dy dx over d squared x over dt squared, and this is a minus dy dx times dx d squared x over dt squared. So since I'm adding and subtracting the same thing, I can actually get rid of that whole term. Okay, and so what do we have left over? Well, this is equal to, we're going to have, so this term is left, d squared y over dt squared, and we have a minus, so minus, and then this term is left, dy dt, and finally this term is left, d squared t over dt squared. And so, hooray, this matches this and yields that. So you can see that using, if you use the correct notation, higher order differentials actually do cancel. They can be used algebraically. This whole idea that higher order differentials or differentials at all shouldn't be used algebraically is a holdover from having bad notation. If you write the second derivative wrong, you'll get the wrong answer if you try to use it. If you try to use it algebraically. Now, I've had some people say, well, we shouldn't take this. You shouldn't tell people that this notation is wrong. It's just notation. And here's the deal. If I were in a math class and I gave an answer as a fraction, and my fraction didn't lead to correct answers, and I said, oh, no, that's just a notation. It's, if you interpret my notation right, then it will work out. And here is a trick for converting my notation to get the right answer. Right? So if I have a notation which requires a trick to work, I view that as bad notation. So the new notation, the chain rule for the second derivative isn't a trick. It's actually just telling you, like someone already solved the problem. They told you how to manipulate things, because we went through and we worked that out. We showed that all of the differentials actually properly cancel each other out. So there's no tricks. It's just straight algebra. So we no longer require tricks. We can use a trick to help us out, but it doesn't violate algebra rules. And so, and the way that we came about this was simply remembering that dy over dx is a quotient. And because of that, we use the quotient rule for taking the derivative of the derivative. So you can do anything you want as long as you do it to both sides. I actually make all of my math students repeat this back to me almost every day. So you can see we have the quotient rule, and when we applied the quotient rule to the actual derivative, then we got back a better notation for the second derivative that actually worked algebraically. And so it's ugly, but it works. So anyway, I hope you check out my paper. It's called Extending the Algebraic Manipulability of Differentials. And I'll have a link to that on the page for this video. Anyway, I hope that people start using this more. And I think, so since we actually do have a trick that allows us to convert from, allows us to do the chain rule on second derivatives, I don't think this is going to correct actual numeric mistakes in mathematics, but I do think it's going to lead us to better understanding what differentials are and how they work, and might lead us to new math that once we start taking differentials more seriously, that we'll be able to dive deeper. Things like, these are things I've always wondered about but haven't had the chance to explore. But let's say we wanted to find the ratio d squared y over d squared x, right? Well, using standard tools, you can't really do that. But using these tools, maybe you can. I don't know that you can, but it's something that's worth asking and worth exploring. So also to note is that you can do this for higher and higher order differentials. They just get uglier and uglier and uglier, and you get more and more terms. Because if I want to find the third derivative, I would have to find the differential of that mess, and divide it by dx. And if I want another derivative, I have to find the differential of whatever that produces and divide it by dx. So these get uglier and uglier as you get higher and higher order differentials. But nonetheless, all the differentials will work out algebraically and will be fully cancelable as long as you know what the notation means. So anyway, I hope that was interesting for you, and I hope to see you back here. I hope you like and subscribe to the video, and have a great day.